Okay, so this is chapter 5, problem 17. Um, you'll notice right away that I've redrawn the figure that we're given. I've kind of combined all of the information that the problem gives us into one spot instead of having it as three sort of separate drawings. And I think that kind of helps to give a better sense of what's going on with all the information sort of overlaid on top of it, on top of itself. So the problem says, refer to the figure. Let the mass of the block be 6.9 kilograms and the angle theta be 39 degrees. Find the tension in the cord and the normal force acting on the block. And then it also says, if the cord is cut, find the magnitude of the block's acceleration. So we're going to do exactly what it says, and we're going to refer to the figure to see what is going on here with this block. And right away, what I want to point out is that um, pointing up and down the slope, so in the direction that's parallel to the slope, you'll notice that the tension and the sine component of the weight are sort of opposite to one another. And you'll also notice that perpendicular to the slope, the normal force and the cosine component of the weight are sort of opposite to each other. So we're going to use that information, and we're also going to sort of extrapolate one more piece of information, and that's how we're going to solve the first part of this problem. So the thing that we're going to have to sort of assume is true, just from what we know about what's happening, is that the block as it sits right now is not moving. So using that information, we can write down two equations. And just from looking at the figure that I've drawn, you can kind of see that they're going to be true. So the first one is that the tension force minus mg sine theta is equal to 0. And also, the normal force minus mg cosine theta is equal to 0. So that kind of has to do with, the block is not moving, and all of these different forces on it have to cancel out for the net force to be 0. And we know that the net force is 0 because it's not moving. So we can rewrite these like this. Okay. And now we're just going to solve for the tension and the normal force. So we are told the mass and the angle. And so we can write this down and solve. So we can say that tension is, the mass would be 6.9 kilograms. Acceleration, just g, 9.8 meters per second squared. And then sine of 39 degrees. And that's going to give us a tension force of 42.6 newtons. So right there is our first answer. For the normal force, it's going to be almost the same thing, just with cosine instead of sine. So the normal force is again the mass, 6.9 kilograms. G is 9.8 meters per second squared. And then we're going to multiply that by the cosine of 39 degrees. That's going to give us a normal force of 52.6 newtons. Oops. Okay, so now we've gotten the sort of first round of answers. But now the question asks, if the cord is cut, find the magnitude of the block's acceleration. And so to do that, we're going to have to write down sort of another relation. And so I'll move back up here. And let's say that the string is cut. So what I'm going to do is just draw a line through it. So let's say we cut that rope, that string. Now the normal force and the cosine component of the weight are still going to cancel out. They're still going to be equal in magnitude, but opposite in direction. But what we've done is we have removed the tension force from this block. And so now the net force is going to be given by this mg sine theta component, because that has nothing opposing it. So hopefully that makes sense. And I'm going to move back down here. And so we can now write that the net force technically these are all vectors. So the net force, which we know is just mass times acceleration, is equal to this mg sine theta term. However, because that points down the slope, we're going to call it negative. So we're going to write it as minus mg sine theta. And we can cancel out the masses like this. And so the net force is going to just say that our acceleration is minus g sine theta. And we can solve that. So the acceleration is minus 9.8 meters per second squared times the sine of 39 degrees. And that's going to give us an acceleration of minus 6.17 meters per second squared. And remember that minus sign is just telling you that it's accelerating down the slope, not up the slope. But the question did ask not for the acceleration itself, but for the magnitude of the acceleration. So just take the absolute value of that. And that's just 6.17 meters per second squared. And that's how you find the third part of the question. So I'll move back up to the problem statement so you can get one last look at that, see what we all did. And that's how you do that. So hopefully that's helpful.